Some of the most powerful forces on Earth aren't man-made. They're alive, they're ancient, and we still can't control them. Throughout human history, we've built cities, conquered diseases, and even reached the moon. We've convinced ourselves that we're masters of our planet. But nature has other plans. Every year, forces beyond our comprehension remind us just how small we really are. Lightning that strikes backwards from the ground to the sky, earthquakes that happen in complete silence, waves that appear from nowhere in calm seas, parasites that turn their hosts into zombies. These aren't science fiction stories. They're happening right now, somewhere on Earth. Today, we're going to explore the natural phenomena that keep scientists awake at night. The forces that can level cities, wipe out species, and change the course of human civilization in an instant. Forces that, despite all our technology and understanding, remain completely beyond our control. Welcome to a world where nature still holds all the cards. Weather gone rogue. Let's start with something we all think we understand. Weather. We check our phones for forecasts. We plan our days around rain and sunshine. But weather has a dark side that most people never see, and it's far more terrifying than any storm you've experienced. In Venezuela, there's a place where lightning strikes the same spot 250 times every minute. The Catatumbo lightning phenomenon occurs where the Catatumbo River meets Lake Maracaibo. For up to 10 hours a night, 300 nights a year, this single location experiences the most intense electrical storm on Earth. Scientists have theories about why it happens here. The unique geography creates a perfect storm of conditions. Methane from oil deposits, wind patterns that collide over the lake, and atmospheric pressure systems that seem designed to create chaos. But here's what keeps meteorologists puzzled. The lightning sometimes just stops. For weeks or months, nothing. Then it returns with no warning, no change in conditions that anyone can detect. We can observe it, we can measure it, but we cannot predict it or control it all. And if you're caught in the middle of it, there's absolutely nothing you can do but hope. Now imagine lightning, but horizontal. Ball lightning is one of the most controversial phenomena in meteorology because it shouldn't exist according to our understanding of physics. Witnesses describe glowing orbs of electricity that float through the air, passing through walls like ghosts, lasting anywhere from seconds to minutes. Some are the size of golf balls, others as large as beach balls. They've been reported since ancient times, but modern science struggled to accept they were real until recent decades. What makes ball lightning truly terrifying is its unpredictability. It can appear during thunderstorms, but also in perfectly clear weather. It can harmlessly bounce around a room, or it can explode with the force of several pounds of dynamite. There are documented cases of ball lightning entering aircraft, floating down the aisle past terrified passengers, then disappearing through the fuselage without leaving a trace. Dr. John Abrahamson, a researcher at the University of Canterbury, spent decades trying to create ball lightning in laboratory conditions. His team managed to produce something similar using silicon particles and electrical discharges, but they still can't explain how it occurs naturally or why it behaves the way it does. Every time they think they understand it, nature shows them something new. But weather's capacity for destruction goes far beyond individual lightning strikes. Fire tornadoes, or firenados, represent the terrifying marriage of two of nature's most destructive forces. When wildfires create their own weather systems, they can spawn rotating columns of flame that reach temperatures of over 2,000 degrees Fahrenheit. These aren't just spinning fires. They're actual tornadoes made of flame, with wind speeds that can exceed 100 miles per hour. The 2018 car fire in California produced a firenado so powerful it was classified as an EF3 tornado. It flipped cars, ripped trees from the ground, and created its own lightning. Fire Captain Mike Hebrard described watching it approach as like seeing hell itself walking across the landscape. The most disturbing part? It moved independently of the main fire, creating its own path of destruction according to atmospheric conditions that forecasters are only beginning to understand. Traditional tornado prediction relies on understanding wind patterns, temperature differentials, and atmospheric pressure. But firenados create their own weather. They generate their own winds, their own pressure systems, their own rules. By the time meteorologists detect the conditions that might create one, it's often too late to warn anyone in its path. Then there's hail that falls like artillery shells. Most people think of hail as annoying ice pellets that might dent your car. But in supercell thunderstorms, hail can grow to the size of softballs, falling at speeds of over 100 miles per hour. In 1986, Bangladesh experienced a hailstorm where individual hailstones weighed over 2 pounds each. 92 people died, and thousands of animals were killed instantly. The physics of how hail grows this large is well understood. Strong updrafts in supercell storms can keep ice pellets suspended in the air for extended periods, allowing them to accumulate layer after layer of ice. But predicting when and where these giant hailstones will form remains largely guesswork. Doppler radar can show us the internal structure of storms, but it can't tell us which storm will produce marble-sized hail and which will drop ice boulders that can kill. Perhaps the most dangerous weather phenomenon that most people have never heard of is the microburst. These are columns of sinking air that hit the ground and spread outward in all directions, creating wind shear that can exceed 150 miles per hour. To aircraft, microbursts are invisible killers. A plane approaching an airport can encounter a microburst and be slammed into the ground with such force that there's no time for pilots to react. Delta Flight 191 experienced exactly this in 1985 while approaching Dallas-Fort Worth International Airport. The Lockheed L-1011 encountered a microburst just 1 mile from the runway. The sudden downdraft pushed the aircraft toward the ground, while headwinds turned to tailwinds in seconds, destroying the lift, keeping the plane airborne. 137 people died in a crash that took less than 10 seconds from the first sign of trouble to impact. Weather radar has improved dramatically since 1985, and airports now have sophisticated wind shear detection systems. But microbursts can form and dissipate in minutes, often too quickly for detection systems to provide meaningful warning. They're invisible to the naked eye, they leave no lasting traces, and they can occur in weather conditions that seem completely normal. The fundamental problem with all these weather phenomena is that Earth's atmosphere is a chaotic system. Small changes in initial conditions can lead to dramatically different outcomes. This is why weather forecasting becomes increasingly unreliable beyond a few days, and why these extreme phenomena remain largely unpredictable despite all our technological advances. We've built Doppler radar networks, satellite monitoring systems, and computer models that can process millions of atmospheric data points per second. Yet nature continues to surprise us with weather events that our models never predicted and our instruments never saw coming. The atmosphere operates on scales from the microscopic to the global, and interactions between these scales create emergent behaviors that we're only beginning to understand. Earth's unpredictable fury. The ground beneath our feet seems solid, permanent, trustworthy. We build our cities on it, our lives around it. But the Earth is constantly moving, shifting, changing in ways that can swallow buildings whole or shake entire continents. And despite all our geological knowledge, the planet still has ways of shocking us. Sinkholes represent one of Earth's most unsettling tricks. The ground simply opens up and swallows whatever happens to be above it. Cars, houses, entire city blocks can disappear in seconds, leaving behind perfectly circular holes that seem to lead straight to the underworld. What makes sinkholes particularly terrifying is how suddenly they appear and how difficult they are to predict. In 2013, Jeffrey Bush was sleeping in his bedroom in Seffner, Florida, when the ground beneath his house suddenly collapsed. His brother Jeremy heard a crash and ran to help, but Jeffrey's entire bedroom had disappeared into a sinkhole 30 feet wide and 60 feet deep. Jeremy tried to jump in after his brother, but other family members held him back as the sinkhole continued to grow. Jeffrey's body was never recovered. The house was demolished, and the sinkhole was filled with gravel, but experts warn that the underlying geological conditions that caused it haven't changed. Florida sits on a foundation of limestone, which dissolves when exposed to slightly acidic groundwater. Over thousands of years, this creates underground caverns and voids. Most of the time, these voids are stable, but changes in groundwater levels, construction vibrations, or simply the passage of time can cause the roof of these caverns to collapse without warning. Ground-penetrating radar can sometimes detect voids, but only if surveyors know where to look. The vast majority of potential sinkholes remain hidden until the moment they open. But sinkholes are nothing compared to the silent earthquakes that can level cities without anyone feeling them coming. Most earthquakes announce themselves with smaller tremors, building to the main event. But some of the most devastating earthquakes in history began with no warning at all. These are called silent earthquakes, and they represent one of the most puzzling phenomena in seismology. The 2011 Tohoku earthquake that triggered the Fukushima disaster was preceded by a silent earthquake that lasted for over a month. The Pacific plate was slowly sliding beneath the North American plate, building tremendous stress. But this movement was so gradual that seismometers barely detected it. When the accumulated stress finally released, it produced a magnitude 9.1 earthquake and tsunami that killed over 15,000 people. Dr. Hiru Kanamori of Caltech has spent decades studying these silent earthquakes. His research shows that they can last for days, weeks, or even months, moving fault lines several feet without producing any detectable shaking. The energy that would normally be released as seismic waves is instead stored as elastic deformation in the surrounding rock. When this stored energy finally releases, it can produce earthquakes far more powerful than the fault's normal activity would suggest. The terrifying implication is that our earthquake monitoring systems, which rely on detecting seismic activity, might miss the build-up to catastrophic events. A fault line that appears quiet and stable might actually be accumulating stress for a devastating earthquake. The Cascadia subduction zone along the Pacific Northwest coast shows evidence of periodic silent earthquakes, and geologists warn that the big one, a magnitude 9 earthquake that would devastate Seattle, Portland, and Vancouver, might arrive with little or no warning. But even known earthquake risks pale in comparison to the supervolcanoes that could end civilization as we know it. Yellowstone National Park sits atop one of the largest volcanic systems on Earth. The Yellowstone caldera is so large that early explorers didn't realize they were standing inside a volcano. The caldera is 34 miles wide and 45 miles long, created by a series of massive eruptions over the past 2.1 million years. The most recent major eruption occurred 640,000 years ago and ejected over 240 cubic miles of material into the atmosphere. Ash from this eruption has been found in fossils as far away as Iowa and Louisiana. If Yellowstone erupted today with similar force, it would cover most of the western United States in ash several feet deep, destroy crops across the entire continent, and trigger a volcanic winter that could last for years. Dr. Michael Poland, the scientist in charge of the Yellowstone Volcano Observatory, monitors the caldera using networks of seismometers, GPS stations, and satellite imagery. The caldera rises and falls by several inches each year as magma moves beneath the surface. Sometimes it rises for several years, then suddenly stops and begins to fall. These movements don't follow any predictable pattern, and they don't necessarily indicate an imminent eruption. The magma chamber beneath Yellowstone is partially molten. Estimates suggest only 5 to 15% is actually liquid rock. For a catastrophic eruption to occur, much more of the chamber would need to melt, a process that would likely take thousands of years and produce clear warning signs. But smaller eruptions remain possible, and even these could have devastating regional effects. What keeps volcanologists concerned is that we have no historical experience with supervolcano eruptions. The last major eruption from a supervolcano was Mount Toba in Indonesia 74,000 years ago, which may have brought humanity to the brink of extinction. We can study the geological evidence, run computer models, and monitor current activity, but we simply don't know how these systems behave in their final stages before eruption. Meanwhile, other parts of Earth are creating tsunami risks that don't depend on earthquakes at all. In 2017, a massive landslide in Greenland's Karat Fjord displaced enough water to create a tsunami 300 feet high. The wave traveled at 400 miles per hour and was detected by seismic monitoring stations around the world. Fortunately, the fjord is remote and sparsely populated, but similar landslides in more populated areas could be catastrophic. Climate change is making these geological tsunamis more likely. As glaciers melt and retreat, they remove support from steep mountain faces that have been stable for thousands of years. Permafrost that has held loose rock in place is thawing, and the additional weight of rainwater in previously frozen ground is destabilizing slopes around the world. Barry Arm Fjord in Alaska shows clear signs of an impending massive landslide. Scientists have identified a section of mountainside containing 500 million tons of rock that is moving toward the water at an accelerating rate. When it falls, not if, but when, it will create a tsunami that could reach Anchorage and threaten coastal communities throughout Prince William Sound. Unlike earthquake-generated tsunamis, which can be predicted once the earthquake occurs, landslide tsunamis happen too quickly for warning systems to be effective. The landslide, the wave generation, and the wave arrival at nearby shores can all occur within minutes. Remote monitoring can identify unstable slopes, but predicting exactly when they will fail remains impossible. The challenge with all these geological phenomena is that Earth operates on timescales far longer than human experience. Events that are incredibly rare from a human perspective, occurring every few hundred or thousand years, are routine from a geological perspective. We've built our civilization during a period of relative geological stability, but that stability is temporary. Our monitoring systems can tell us about current conditions and recent changes, but they can't account for processes that unfold over centuries or millennia. The earthquake that devastates a city might be the culmination of stress that has been building for 500 years. The volcanic eruption that changes global climate might be the result of magma chamber processes that began before recorded history. Biological forces. We can't stop. Nature's most insidious weapons aren't tsunamis or earthquakes. They're microscopic, they're patient, and they're already among us, waiting for the right moment to strike. Biological forces represent some of the most unpredictable and unstoppable threats our planet faces, and many of them are getting stronger while our defenses grow weaker. Fungal infections are silently wiping out entire species across the globe, and scientists are increasingly concerned that humans might be next. White nose syndrome has killed over 6.7 million bats in North America since 2006. The fungus, Pseudogymnoascus destructans, grows on the muzzle and wings of hibernating bats, disrupting their sleep cycles and causing them to starve to death. Entire caves that once housed thousands of bats now lie empty and silent. But that's just the beginning. Chytrid fungus has driven over 200 amphibian species to extinction, making it responsible for the greatest loss of biodiversity attributable to a single disease in recorded history. BD, as scientists call it, attacks the skin of frogs and salamanders, disrupting their ability to breathe and regulate water balance. What makes it unstoppable is its ability to survive in water and soil indefinitely, waiting for new hosts. Dr. Erica Bree Rosenblum at UC Berkeley studies how these fungal pathogens spread and evolve. Her research reveals that climate change is creating perfect conditions for fungal outbreaks. Warmer temperatures are expanding the range where these pathogens can survive, while environmental stress is weakening the immune systems of potential hosts. Even more concerning, the fungi themselves are evolving, becoming more virulent and developing resistance to antifungal treatments. The nightmare scenario that keeps epidemiologists awake at night is a fungal pathogen that jumps to humans. This isn't science fiction, it's already happening. Candida auris, a multi-drug-resistant yeast, has spread to hospitals worldwide in just a few years. It's resistant to most antifungal medications. It can survive on surfaces for weeks, and it has a mortality rate of 30 to 60%. Hospital outbreaks have been so severe that entire wards have had to be closed for intensive decontamination. What makes fungal infections particularly terrifying is that we have very few effective treatments. While we have dozens of antibiotics to fight bacterial infections, there are only 3 major classes of antifungal drugs. Fungi are eukaryotes, like humans, which means that drugs effective against them often damage human cells as well. And fungi are masters of adaptation. They can quickly develop resistance to whatever treatments we throw at them. Meanwhile, other organisms are demonstrating collective intelligence that rivals human societies, and they're using it for conquest. Army ants don't just march, they think collectively, solve problems, and adapt their strategies in real time. When army ants encounter a river during their raids, they do something that seems impossible. They build living bridges using their own bodies. Worker ants link together to form chains across the water, allowing the rest of the colony to cross safely. But here's what makes it truly remarkable. The bridge ants don't just passively hold position. They actively adjust the bridge's structure based on traffic flow, shortening it when fewer ants need to cross, extending it when traffic increases. They're performing complex engineering calculations using nothing but simple behavioral rules and local communication. Dr. Chris Reed at the University of Sydney has studied how these living structures form and adapt. His research shows that army ant colonies can solve optimization problems that would challenge human engineers. They find the shortest path between food sources and their nest. They allocate workers efficiently across multiple tasks, and they can rapidly reorganize when faced with obstacles or threats. But during floods, army ants do something even more extraordinary. They form living rafts. Thousands of ants lock their legs and mandibles together, creating a waterproof platform that can float for weeks if necessary. The ants on the bottom of the raft will eventually drown, but the colony survives. It's a level of sacrifice and collective action that human societies struggle to achieve even in the face of existential threats. These aren't mindless insects following simple programming. Army ant colonies demonstrate emergent intelligence, complex behaviors that arise from the interactions of many simple agents. They can plan attacks, execute coordinated maneuvers, and adapt their strategies based on experience. And they are just one example of how biological systems can organize themselves in ways that surpass human understanding. Locust swarms represent another form of collective behavior that can overwhelm human defenses through sheer numbers and coordination. A single desert locust swarm can contain up to 80 million locusts per square mile and cover areas larger than major cities. The largest swarms have been tracked by satellite across multiple countries, devouring crops and vegetation across hundreds of thousands of square miles. What transforms solitary grasshoppers into swarming locusts is still not fully understood. The change appears to be triggered by overcrowding and resource scarcity, but the specific mechanisms involve complex interactions between genetics, behavior, and environmental conditions. When the transformation begins, it's like a switch flips. The insect's entire biology changes, their color changes, their behavior becomes more aggressive, and they begin to produce pheromones that attract other locusts from vast distances. Keith Cressman, Senior Locust Forecasting Officer for the UN Food and Agriculture Organization, tracks swarm movements using satellite imagery and weather data. But predicting where swarms will go next remains largely guesswork. Locust swarms can travel over 100 miles in a day, and they don't follow predictable patterns. They respond to wind currents, food availability, and breeding conditions in ways that create chaotic, unpredictable movements. Recent swarms in East Africa have been particularly devastating. In 2020, swarms containing billions of locusts consumed crops across Kenya, Ethiopia, and Somalia, threatening the food security of millions of people. The swarms were so large they could be seen from space, darkening the sky for hours as they passed overhead. Despite modern monitoring systems and pesticide spraying operations, the swarms caused hundreds of millions of dollars in agricultural damage. But perhaps the most disturbing biological force is the one that turns other organisms into zombies. Parasites that manipulate host behavior are more common than most people realize, and their control mechanisms are becoming increasingly sophisticated as we study them more closely. Ophiocordyceps fungi infect ants and take control of their nervous systems, forcing them to climb to specific locations and heights before killing them. The fungus then grows a fruiting body out of the ant's head, positioned perfectly to spread spores to other ants below. But recent research has revealed that different species of Ophiocordyceps are specialized for different ant species and different environments, suggesting a level of evolutionary refinement that scientists are only beginning to understand. Dr. David Hughes at Penn State University studies these zombie ant fungi and has discovered that the parasites don't just control behavior, they reshape the entire biology of their hosts. The fungus infiltrates the ant's brain, muscles, and organs, essentially turning the ant into a fungal extension. The ant remains alive throughout most of this process, aware but no longer in control of its own actions. Similar parasites affect many other species. Toxoplasma gondii infects rats and makes them lose their fear of cats, increasing the likelihood that they'll be eaten, and the parasite can complete its life cycle in the cat's intestines. But Toxoplasma also infects humans, and studies suggest it may influence human behavior as well, potentially affecting risk-taking, reaction times, and even personality traits. Hairworms manipulate crickets and grasshoppers, compelling them to seek out water and drown themselves so the worm can emerge and reproduce in aquatic environments. The worm produces proteins that affect the insect's brain chemistry, essentially hijacking its survival instincts. What's particularly disturbing is that these parasites can make their hosts act against every evolutionary drive they possess. The mechanisms by which these parasites control behavior are becoming clearer through advances in neuroscience and molecular biology. But this knowledge also reveals how sophisticated these control systems have become through millions of years of evolution. Each parasite has developed specific biochemical tools to manipulate its particular host species, and many can fine-tune their control based on environmental conditions and the host's physiological state. What keeps researchers concerned is that these biological control systems represent a form of natural biotechnology that far exceeds anything humans have developed. If similar mechanisms could affect humans more broadly, or if existing human parasites evolved more sophisticated control mechanisms, the implications would be catastrophic. The fundamental challenge with biological forces is that they evolve. Unlike geological or meteorological phenomena, biological threats can adapt to our defenses, develop new capabilities, and spread in ways that weren't possible before. Climate change, global travel, habitat destruction, and antibiotic resistance are all creating conditions that favor the emergence and spread of new biological threats. Our medical and agricultural systems are built on the assumption that we can stay ahead of biological threats through technology and scientific understanding. But evolution never stops, and biological systems can adapt far more quickly than human institutions can respond. The next pandemic, the next crop disease, or the next invasive species might be unlike anything we've seen before, with capabilities that our current defenses never anticipated. Space versus nature. While we worry about threats on Earth's surface, space is preparing its own arsenal of destruction. The cosmos operates according to forces so vast and energetic that they make terrestrial disasters look insignificant by comparison. And unlike earthquakes or hurricanes, space-based threats can strike without warning, affecting the entire planet simultaneously. Solar flares represent one of the most immediate space-based threats to modern civilization. The sun is essentially a massive nuclear reactor, and sometimes that reactor experiences violent outbursts. Solar flares are magnetic explosions on the sun's surface that release energy equivalent to billions of hydrogen bombs. When these explosions are directed toward Earth, they can arrive in as little as 8 minutes at the speed of light. The 1859 Carrington event was the most powerful geomagnetic storm in recorded history. Telegraph systems around the world failed catastrophically. Some operators received electric shocks, telegraph paper caught fire, and some telegraph systems continued working even after being disconnected from their power sources, running purely on induced current from the geomagnetic disturbance. Aurora lights were visible as far south as the Caribbean, so bright that people could read newspapers by their light. Dr. Daniel Baker at the University of Colorado studies space weather and its effects on technological systems. His research shows that a Carrington-level event today would be catastrophic for modern society. The electrical grid would suffer widespread failures. Satellites would be damaged or destroyed, GPS systems would become unreliable, and communication networks would experience severe disruptions. The economic impact could exceed $2 trillion, and recovery could take years. What makes solar flares particularly concerning is their unpredictability. The sun follows an 11-year cycle of activity, but major flares can occur at any point in the cycle. Solar activity monitoring has improved dramatically in recent decades, with satellites positioned between Earth and the sun to provide early warning. But even with advance notice, there's little we can do to protect most of our infrastructure. In 2012, a solar flare more powerful than the Carrington event missed Earth by just 9 days. If our planet had been in the path of that coronal mass ejection, the results would have been devastating. The plasma cloud traveled through space at over 4 million miles per hour, and if it had hit Earth, it would have caused the most severe geomagnetic storm in human history. The challenge with solar flares is that our technological civilization has become completely dependent on systems that are vulnerable to electromagnetic interference. Power grids, satellites, computers, and communication networks all use sensitive electronic components that can be damaged or disrupted by geomagnetic storms. We've built a world that can be brought to its knees by events occurring 93 million miles away. But solar flares are mild compared to the cosmic radiation that constantly bombards our planet. Galactic cosmic rays are high-energy particles that travel through space at nearly the speed of light. They originate from supernovas, black holes, and other violent cosmic events, and they can penetrate almost any material. Earth's magnetic field and atmosphere provide some protection, but high-energy cosmic rays regularly reach the surface. These cosmic rays have been shaping life on Earth for billions of years. They cause genetic mutations, some beneficial, some harmful. They may have played a role in major evolutionary leaps, and they continue to affect the evolution of life today. But they also pose risks to modern technology and human health, particularly for astronauts and airline crews who spend significant time at high altitudes where atmospheric protection is reduced. Dr. John Biersack at NASA studies cosmic ray effects on human health and spacecraft systems. His research shows that cosmic rays can cause single-bit errors in computer memory, leading to system failures in satellites and aircraft. More concerning, cosmic rays can cause cancer and other health problems in humans, and the risk increases significantly outside Earth's protective magnetic field. Recent studies suggest that cosmic ray intensity varies over geological timescales, potentially influencing mass extinction events. When our solar system passes through different regions of the galaxy, or when nearby supernovas occur, the cosmic ray environment around Earth changes dramatically. Some researchers propose that increased cosmic ray exposure contributed to the extinction of the dinosaurs and other mass extinction events throughout Earth's history. Meanwhile, Earth's magnetic field itself is showing signs of instability that could leave us more vulnerable to both solar and cosmic radiation. The magnetic North Pole has been moving at an accelerating rate, traveling over 40 miles per year toward Siberia. The magnetic field has also been weakening. It's lost about 10% of its strength over the past 150 years. Dr. Kieran Beggan at the British Geological Survey monitors Earth's magnetic field using ground-based observatories and satellite data. His research shows that the magnetic field is becoming increasingly chaotic, with areas of rapid change appearing in unexpected locations. The South Atlantic anomaly, a region where the magnetic field is particularly weak, has been growing and moving westward. These changes suggest that Earth might be approaching a magnetic field reversal, an event where the north and south magnetic poles switch positions. Magnetic reversals have occurred many times throughout Earth's history, but the process is poorly understood. Reversals can take thousands of years to complete, during which the magnetic field becomes weak and chaotic, leaving Earth more vulnerable to cosmic radiation. A magnetic field reversal wouldn't directly threaten human survival. Humans existed during previous reversals, but it could have severe effects on technology and possibly climate. Satellites would face increased radiation exposure, power grids would experience more frequent geomagnetic storms, and the atmosphere's chemistry could change in ways that affect weather patterns. Perhaps the most existential space-based threat comes from asteroid impacts. Earth exists in a cosmic shooting gallery, with thousands of near-Earth asteroids large enough to cause significant damage. The asteroid that killed the dinosaurs was about 6 miles in diameter, but much smaller objects can still cause catastrophic regional damage. The 2013 Chelyabinsk meteor was only about 65 feet in diameter, but it exploded with the force of 30 Hiroshima bombs. The blast wave damaged buildings across 6 cities, injured over 1,500 people, and created a shock wave that traveled around the Earth twice, and nobody saw it coming. The asteroid approached from the direction of the sun, making it essentially invisible to ground-based telescopes until it entered the atmosphere. NASA's Planetary Defense Coordination Office tracks near-Earth asteroids and has catalogued over 25,000 objects larger than 450 feet in diameter. But this represents only a fraction of the potentially hazardous asteroids in our solar system. Smaller objects, like the one that hit Chelyabinsk, are much more numerous and much harder to detect. Dr. Lindley Johnson, NASA's Planetary Defense Officer, oversees efforts to identify and track potentially hazardous asteroids. His team has developed the Double Asteroid Redirection Test, DART mission, which successfully changed the orbit of an asteroid by crashing a spacecraft into it. But this technology is still in its infancy, and it would only be effective against asteroids detected years in advance. The fundamental problem with asteroid detection is that space is vast and dark. Asteroids don't emit light. They only reflect sunlight, and many are so dark they reflect less than 5% of the light that hits them. Detecting a dark object a few hundred feet across at distances of millions of miles is extraordinarily difficult, especially when that object might be moving at speeds of tens of thousands of miles per hour. Recent discoveries have made the asteroid threat even more concerning. Some asteroids are actually loose collections of rubble held together by gravity, making them virtually impossible to deflect using current technology. Others have highly elliptical orbits that bring them close to Earth only rarely, meaning they spend most of their time too far away to be easily detected. The space environment around Earth is also becoming increasingly dangerous due to human activity. There are over 34,000 pieces of trackable space debris in orbit around Earth, and millions of smaller pieces that can't be tracked but are still large enough to damage or destroy satellites. This debris travels at speeds of up to 17,500 miles per hour, making even tiny fragments extremely dangerous. The Kessler syndrome describes a scenario where the density of space debris becomes so high that collisions between objects create more debris, leading to a cascade of collisions that makes entire orbital regions unusable. Some experts believe we're already seeing the early stages of this process, as the number of satellites and debris objects continues to increase exponentially. What makes space-based threats particularly challenging is the scale of both space and time involved. Events that affect Earth might originate from billions of miles away and take years to reach us, or they might travel at the speed of light and arrive with no warning. The forces involved, from stellar explosions to planetary impacts, operate on energy scales that dwarf anything on Earth's surface. Our ability to predict and respond to space-based threats is improving, but we're still essentially helpless against most cosmic events. We can detect some asteroids, we can monitor solar activity, and we can track some space debris. But the universe contains forces and objects that could end human civilization in an instant, and we would never see them coming. The ones we never saw coming. The most terrifying natural forces aren't always the most obvious ones. Sometimes nature's deadliest weapons are phenomena so rare, so unexpected, or so poorly understood that they catch scientists completely off guard. These are the forces that remind us how much we still don't know about our own planet. Beneath the ice of Antarctica, something called a brinnacle forms that looks like nothing else on Earth. Underwater footage reveals what appears to be a finger of ice reaching down from the surface, growing longer and longer until it touches the sea floor. But this isn't just ice. It's a weapon of mass destruction for any small creature unfortunate enough to be in its path. Brinnacles form when extremely cold, Salt-rich water sinks through less salty seawater. The temperature difference is so extreme that the descending brine actually freezes the less salty water around it, creating a hollow tube of ice that extends toward the sea floor. When a brinacle reaches the bottom, the supercooled brine spreads outward, instantly freezing everything it touches. Starfish, sea urchins, and other bottom-dwelling creatures become trapped in ice within seconds, creating an underwater graveyard. Dr. Andrew Thurber, a marine biologist who has studied brinicles in Antarctica, describes them as nature's icicles of death. The process requires such specific conditions, precise temperature gradients, salinity differences, and water currents, that brinicles were only captured on film for the first time in 2011, despite decades of Antarctic research. They form rarely and unpredictably, and they can appear in locations where the seafloor ecosystem has never experienced such an event. What makes brinicles particularly unsettling is that they represent a completely different mechanism of environmental change. Most ecological disasters unfold over months or years, giving organisms some chance to adapt or escape. Brinicles create ecological death zones in minutes, with no warning and no possibility of escape for bottom-dwelling creatures caught in their path. Meanwhile, beneath the ocean in other parts of the world, pockets of methane create time bombs that can explode without warning. Methane hydrates form naturally on the sea floor under conditions of high pressure and low temperature, creating what looks like ice but burns when ignited. These deposits contain enormous amounts of energy. A single cubic foot of methane hydrate contains 164 cubic feet of natural gas. But methane hydrates are stable only under very specific conditions. Changes in water temperature, pressure, or chemistry can cause them to decompose rapidly, releasing massive amounts of gas. When this happens underwater, the results can be catastrophic. The Deepwater Horizon disaster in 2010 wasn't just about oil. It also involved massive releases of methane that had been trapped in hydrate deposits beneath the sea floor. The drilling operation destabilized these deposits, contributing to the violence of the blowout that killed 11 workers and created the largest marine oil spill in history. Dr. Carolyn Ruppel at the U.S. Geological Survey studies methane hydrates and their potential for sudden release. Her research shows that climate change is destabilizing hydrate deposits around the world as ocean temperatures rise and currents change. The Arctic Ocean, in particular, contains vast methane hydrate deposits that are becoming increasingly unstable as Arctic waters warm. When methane hydrates decompose rapidly, they can create underwater avalanches that trigger tsunamis. The Storegga slide, which occurred off the coast of Norway about 200 years ago, may have been triggered by methane hydrate destabilization. The underwater landslide moved 290 cubic miles of sediment and created a tsunami that reached Scotland, some 400 miles away. But methane releases don't just create immediate physical dangers, they can also suffocate everything in the surrounding area. Methane is lighter than water and rises rapidly to the surface, but in the process, it displaces oxygen-rich water. Fish and other marine life caught in a methane plume can suffocate within minutes, creating massive die-offs that seem to appear from nowhere. Even more terrifying are the methane releases that occur on land. In 2014, mysterious craters began appearing in the Siberian tundra, some over 200 feet wide and 300 feet deep. These craters are created by methane explosions beneath the permafrost. As the permafrost melts due to climate change, it releases methane that has been trapped for thousands of years. This methane can accumulate beneath the remaining frozen layer until pressure builds to explosive levels. Local residents report hearing loud booms and seeing flashes of light before these craters appear. The explosions are powerful enough to hurl frozen chunks of earth hundreds of feet in all directions. What's particularly concerning is that these explosions are becoming more frequent as Arctic temperatures rise, and they're occurring in areas where people live and work. In the middle of the ocean, far from any storm systems, rogue waves appear that defy every model of how waves are supposed to behave. These waves can reach heights of over 100 feet, appearing suddenly in otherwise calm seas. For centuries, sailors reported encounters with massive waves that seemed to come from nowhere, but scientists dismissed these accounts as folklore or exaggeration. The MV München, a 860-foot cargo ship, encountered a rogue wave in the North Atlantic in 1978. The wave was so large and powerful that it bent the ship's steel hull and tore off its superstructure 60 feet above the waterline. The ship broke apart and sank, killing all 28 crew members. An investigation found that only a wave over 100 feet tall could have caused the damage pattern observed on the recovered wreckage. Dr. Susanne Lehner at the German Aerospace Center uses satellite radar to study rogue waves. Her research has confirmed that these waves are far more common than previously thought. Satellite data reveals several rogue waves occurring somewhere in the world, oceans every day. They can appear in any weather conditions, often in areas where wave models predict much smaller waves should exist. What makes rogue waves so dangerous is their unpredictability. They don't form according to the normal rules of wave physics. Most waves are created by wind and follow predictable patterns based on wind speed, duration, and distance traveled. But rogue waves can form through the constructive interference of multiple wave trains, creating a single wave that's much larger than any of its components. Recent research suggests that rogue waves might also be influenced by ocean currents, underwater topography, and even the Earth's rotation through complex mechanisms that scientists are only beginning to understand. Some rogue waves appear to be focusing effects, where the ocean acts like a lens, concentrating wave energy into a single massive peak. But perhaps the most horrifying natural phenomenon that most people have never heard of is the limnic eruption, where lakes literally explode, releasing clouds of suffocating gas that can kill everything for miles around. Lake Nyos in Cameroon experienced such an eruption in 1986, releasing over 100 million cubic meters of carbon dioxide in a matter of hours. The carbon dioxide, being denser than air, flowed down the valleys surrounding the lake like an invisible river of death. It suffocated 1,746 people and thousands of animals across an area of over 100 square miles. Survivors described seeing the lake change color and hearing a rumbling sound before losing consciousness. Many people died in their sleep, never knowing what was happening. Dr. George Kling from the University of Michigan has studied limnic eruptions and the conditions that make them possible. Deep lakes in volcanic regions can accumulate dissolved gases, primarily carbon dioxide, in their bottom layers. Under normal circumstances, these gases remain dissolved due to the pressure of the water above them. But if something disturbs the lake, an earthquake, landslide, or even strong winds, the gases can suddenly come out of solution, like opening a shaken bottle of soda. The Lake Nyos eruption was preceded by a landslide that disturbed the lake's stratified layers. Once the process began, it became self-sustaining. The rising gas bubbles reduced the pressure on the water below, causing more gas to come out of solution. The entire event lasted only a few hours, but it released gas that had been accumulating in the lake for decades. What makes limnic eruptions particularly terrifying is that they can occur with little or no warning. Lake Kivu, on the border between Rwanda and the Democratic Republic of Congo, contains vastly more dissolved gas than Lake Nyos ever did. Over 2 million people live in the area around Lake Kivu, and the lake shows signs of increasing instability. A limnic eruption there could kill hundreds of thousands of people. Attempts to prevent limnic eruptions by slowly releasing dissolved gases have had mixed success. Lake Nyos now has a fountain system that brings deep water to the surface, allowing gas to escape gradually. But these systems are expensive, require constant maintenance, and may not be sufficient for larger lakes or more violent eruptions. Scientists have identified several other lakes around the world that could potentially experience limnic eruptions. Lake Manaon in Cameroon killed 37 people in a smaller eruption in 1984. Volcanic lakes in Indonesia, Italy, and other regions show similar chemical signatures. The conditions that create these deadly lakes are more common than once thought, and climate change may be making eruptions more likely by altering lake temperatures and circulation patterns. The fundamental problem with all these phenomena is that they occur so rarely that we have very little data about them. Brinicles might form only a few times per year in specific Antarctic locations. Methane explosions in permafrost are a newly observed phenomenon with no historical precedent. Rogue waves last only minutes and occur in remote ocean areas where they're rarely witnessed. Limnic eruptions might happen only once per century in any given lake. This rarity makes it almost impossible to predict when and where these events will occur next. We can identify the general conditions that make them possible, but the specific triggers often remain mysterious. A small earthquake, a temperature change of a few degrees, or a shift in atmospheric pressure might be enough to trigger a catastrophic event, but we can't predict which small change will be the one that matters. These rare phenomena also challenge our assumptions about how the natural world works. We build our understanding of nature based on common events and regular patterns, but the rare events often operate according to different rules entirely. They remind us that Earth is still capable of surprising us, even in an age when we think we've mapped and measured everything. Nature doesn't follow our rules. We follow hers. Throughout this exploration of Earth's most terrifying natural forces, one truth emerges repeatedly. Despite all our scientific advances, despite our sophisticated monitoring systems and computer models, the natural world remains largely beyond our control. We've sent spacecraft to other planets, decoded the human genome, and built computers that can beat grandmasters at chess. Yet we still can't predict when the next major earthquake will strike, when a supervolcano might erupt, or when a solar flare will knock out our power grids. We can't stop a hurricane, prevent a pandemic, or deflect most asteroids. We can observe, we can measure, and sometimes we can prepare, but we cannot control. The forces we've examined today operate on scales from the microscopic to the cosmic, from the depths of the ocean to the edge of space. They've been shaping our planet for billions of years, long before humans existed, and they'll continue long after we're gone. What makes them particularly humbling is that many of them are getting stronger or more frequent due to human activities, even as our ability to respond to them lags behind. Climate change is destabilizing methane deposits, weakening polar ice, and creating conditions for more severe weather events. Global travel is spreading diseases and invasive species faster than ever before. Light pollution and space debris are making it harder to detect incoming asteroids. Our increasing dependence on technology makes us more vulnerable to solar flares and electromagnetic disturbances. Yet perhaps the most sobering realization is how much we still don't know. Every year, researchers discover new phenomena that don't fit existing models. Every disaster teaches us something unexpected about how the world works. Every rare event reminds us that our understanding of nature is built on incomplete data and imperfect theories. The scientists and researchers whose work we've explored today aren't pessimists or alarmists. They're people who have dedicated their lives to understanding these forces, to finding ways to predict them, and to helping humanity prepare for them. Their message isn't that we should live in fear, but that we should live with humility and respect for the planet we call home. The next chapter in humanity's relationship with these natural forces is still being written. We're developing better monitoring systems, more sophisticated models, and new technologies for prediction and response. But we're also creating new vulnerabilities and triggering changes in Earth's systems that we don't fully understand. The forces we've discussed today, the lightning that strikes without warning, the ground that opens beneath our feet, the organisms that turn others into zombies, the space rocks that could end civilization. They're all part of the same planet we call home. They're reminders that we're not separate from nature. We're part of it. And nature, in all its terrible beauty, will always hold surprises we never saw coming. As you go about your daily life, remember that you're living on a dynamic, unpredictable planet in a vast and violent universe. The ground beneath your feet has moved thousands of miles from where it formed. The air you breathe has been recycled through countless organisms over billions of years. The elements in your body were forged in the hearts of dying stars. You're part of an incredible, complex, and dangerous system that we're only beginning to understand. And that system, for all its terrors, is also the only home we've ever known. The same forces that can destroy us have also created us, sustained us, and made possible every moment of beauty and wonder in human experience. The story of humanity is the story of learning to live with forces beyond our control, of finding ways to thrive despite constant threats, of building civilization on a foundation that's always shifting beneath our feet. It's a story that's still being written, with each new discovery, each new disaster, and each new day we survive on this remarkable and terrifying planet we call Earth. Nature doesn't follow our rules, but maybe, just maybe, we can learn to follow hers.